Okay, so good morning everyone. So now it is 11:03. So I believe that the majority of students are already in the call. So I will give 1 more minute for you guys to scan the QR code. And then we will start with our lecture. So first of all, can you hear my voice?
Um, yes, Doctor.
Yes. Okay. All right. Thank you. So basically for today, you need to bear with me because this chapter is quite not that long, but it's quite heavy. So please bear with me lah. Okay. All right. So that's why I need to start right away. All right. So now it's 11:04. I believe that we can start now. Okay. So can you see the slides? Nampak eh? Okay, alright. Thank you. Alright, so sorry. Alright, so basically, last week we have looked at into the sample preparation for spectroscopic methods. So basically now we are going to look at into the sample analysis. Means that we have gone through on how are you going to handle the sampling process during chapter 1, and then you look into on how are you going to do the preservation, the storage, and then you looked at into apa all of the all of the instruments, the UV visible, flame AAS, and then ICP-MS. And then you also have looked into the how to prepare the sample prior to the analysis. So now we are going to look into on what happens after the analysis. So what are you going to do with it? All right. So how are you going to interpret, or how what are you going to do in terms of for you to be able to quantify it later on? Okay. All right. So, moving on to the second slides. Okay, basically, for the analytical process, we we are now looking at into the sample analysis, where the sample analysis we measure the analyte in a several identical aliquots. Means that you need to have replicates measurements. Okay, replicate measurement usually inside analytical process. The normal way is that for you to do it triplicates, so 3 times. Okay, 3 times analysis per analyte. Okay, per sample. All right. So this replicate measurement would reduce the uncertainty in your analysis, where we will avoid large errors, and hence your measurement would be much more reliable. Okay, so that's the first thing. The second thing, when you do your sample analysis, we need to have a calibration curve. Okay, what does it mean by a calibration curve? Or we call it a calibration graph. Okay, calibration curve means that you measure the response of your known sample. Okay, means that now you say that known samples. Known samples means that sample that you know the concentration. Okay, let's see for this apa? For this graph. This graph is an example of a calibration curve. Okay, calibration curve means that you need to create a series of standards with different kind of concentration. For example, you create 1 ppm, 5 ppm, 10 ppm, and 20 ppm. So you have 1, 5, 10, and 20. So when you do your analysis, you already know that the concentration is keep on increasing kan, from 1 until 20. So your response also will be in an increasing order. All right. So when you do that, you will create some sort like a graph. Okay. An absorbance or intensity which is corresponding to the your nilah apa your concentration that you have prepared earlier. So with that calibration graph, with that calibration curve, you would be able to determine your unknown sample. Okay. I know it's hard to apa orang kata tu to imagine it right now. After this, we will be looking at it. But the function of a calibration curve is that for you to measure the response of your known samples. Okay. Known samples here, you need to understand that to form a calibration graph or a calibration curve, you need to use standard with known concentration. You yourself know the concentration of it. All right. All right. So okay, so this is an example of a calibration curve, the graph as well. So calibration curve of signal versus concentration. Okay, you look here. You look through this graph. This is a graph of response with this y-axis and then concentration with which is your x-axis. Okay, so now for this calibration curve, it has been prepared for the calibration curve to become 1, 2, 3, 4, 5. Okay, as what my example just now, 1, 5, 10, 20. Tapi tak apa, it's okay. It's just that we want to look at into the pattern. Okay, you prepare your standard at 1 ppm, 2 ppm, 3, 4, 5 ppm. And then when you do your analysis, you've got this uh, yes, analytical signal is the same as response. All right. So when you create your first your 1 ppm here, it will give a response here, maybe a 0.06. And then as it goes, as the concentration increases, your response also will increases. Okay, which is logically that's how you should get lah. When you have an increased concentration, your response also will be increased. So when you have this kind of plot where it is continuously increasing, you can create a straight line where the straight line will pass through most of the points here, where you would create some sort of an equation and have some slope and also some intercept. So now, so this is a calibration curve with known concentration here, and you have got your response. You create your straight line here, and here you've got your equation here. So the function of calibration curve is just a simple thing, is that, okay, now you have your unknown, you have your sample, you don't know the concentration, so you do this analysis. Okay, but suddenly the unknown would give you a response at 0.2. Okay, so when you have your 0.2 here, response from your unknown, you just go back to the calibration curve. You just plot it straight here until it meet up to the to the your calibration curve here, your straight line here, and then you just go down to the concentration, and you've got your apa your concentration of the unknown here, which is around 3.3 ppm, something like that. Okay, up until this point, faham tak? Did you guys understand in terms of the function of calibration curve here? Do you guys have any question for this? Ada ke tak faham? Because now I want to create some sort of like a apa? Uh, for you to understand first in terms of, okay, what is the function of calibration curve actually, and how does it work? Okay, all right. All right, so I will continue on the calibration graph. So now this is the explanation of the calibration graph lah, which I have explained before. Okay, so the calibration curve is that graph showing the analytical response as a function of the known quantity of the analyte. So known quantity here. All right, so it is necessary to interpret the response for unknown quantities. So as what I've mentioned before, you can use the calibration graph for you to be able to interpret the unknown quantities. Okay, you quantify the unknown sample. All right, so the y vertical axis is an instrument response, and the x is the concentration. Okay, the calibration curve are normally linear. However, not all of the points are located on the drawn straight line due to the random error. Okay, so basically when you look at this line, not all of the points does the straight line move through kan. So this point here, the fourth points, uh, the straight line just touches the point. Okay, this is due to the random error lah. So you would not be able to get a perfect line. All right. So, regression analysis can be done on the data to see how good the linearity of the data by using method of least squares. All right, so this method of least squares, you can do this inside Excel when you have your data later on. Okay, so because it will create some sort like a regression analysis for you to be able to know whether your straight line here is good or not. Okay, good means that uh, for now you were able to determine you were able to think that good means that it moves through all the points. Okay, that's good basically, but there is a there is a way on how you quantify good is it. Okay, we will look at later on. All right, there are three types of calibration. All right, so there are external calibration, standard deviation calibration, and internal standard calibration. All right, so for this chapter, you would be able to just look at into external calibration and standard deviation calibration. For internal standard calibration, this will be explained further during your chromatography uh, chapter later on. All right. Okay, so now there are some terms here that you need to know, and you need to know in terms of the definition. Okay, basically what are the reagent blank? All right, so who wants to explain what is the reagent blank? Reagent blank, sorry. Anyone? Anyone ada rasa nak explain what is the reagent blank? What do you understand about reagent blank? Arif Fahmi. Tak apa, salah pun tak apa, kita belajar.
Ya,
Doctor,
Okay. What is the reagent blank?
uh, saya tak pasti lah doktor. Sure.
Just a guess. Apa benda? Tahu tak?
Hmm, tak tak sure lah doktor.
Alright. So anyone else? Ya nak try?
Doctor, but also I'm not sure. Is it a sample of the sample just to test it, or
Sorry, Faisal. I could not hear you clearly. What does it mean
uh,
by reagent blank just now?
is it like the sample of the sample? I'm not sure actually if it's correct or not.
Okay. So basically, reagent blank here, it is defined as that. Um, okay, blank. Okay, blank means that your matrix means that it is analyte free. Alright, so the blank test must be carried out in parallel with the determination by the same procedure but omitting the test portion. Means that your blank, your reagent blank here must be a solution that is without your analyte. So whatever, whenever that we are talking blank in any kind of thing, when we're talking about blank, it must be analyte free. It is a solution that must be free from your analyte of interest. For example, okay, for example, you you want to analyze sodium in a seawater. Okay, so your sample must be seawater with sodium. Your blank must be seawater without sodium because we don't want the sodium to have we don't want your blank to have some sort like a value for sodium later on. Okay, the blank must be free from analyte. Okay, do you guys understand about reagent blank? It must be analyte free. It's a solution or it is a reagent without your analyte of interest. All right. Okay. So now we are going to look at, okay, what is analysis ready sample? Analysis ready sample is that your sample, before this we have looked into the sample preparation kan. So the sample preparation, it looks into the digestion lah, ashing, dry ashing. So when your sample has been done, all of those have been gone through all of the digestion solution, and you dilute your digested solution in with ultra pure water to a known volume, for example 25 ml volumetric flask. So those solution is called analysis ready solution. Okay, so it is called analysis ready solution, but may ensure that your analysis ready solution must be clear. Okay, there is no turbidity ataupun deep color in your analysis ready solution, because those turbidity, those uh, unclear color would create some sort like a incomplete digestion lah. It means that there is an incomplete digestion. So if there is an incomplete digestion, if there is a solid inside your analysis ready solution, hence it will be aspirated into your instrument, which will create some sort like an error. Okay. All right. Reagents. Okay, reagent here, we have also looked into a reagent before this. High purity reagents, even in your digestions also, we have looked into high purity reagents for your acids. Okay, so why high purity reagents? It needs to be free from interferences. Okay, so we don't want your reagents to create some sort like interferences for your analysis later on. All right. So, what are the standard stock or internal solution? So, standards means that usually something that we've um, bought. Okay, standard. So usually for standards, it has been sold at maybe about 1000 ppm. Okay, so that is your standard stock. Okay, so usually we will use this standard to create your calibration curve later on. Okay, so your standard would have some sort like a known quantity. Okay, so maybe 1000 ppm, and then you use that standard 1000 ppm, you dilute it to become 1 ppm. Okay, that is your standard stock. Calibration standard, okay, it is something that you've got from your standard stock lah. Fresh calibration standard should be prepared every day or as needed. Okay, so these are the terms that are going to be used a lot in this chapter with their definition. All right, so okay, so basically now we are going to look at into how are we going to let's say define whether your straight line 2 is straight or your calibration curve is good. Okay, it depends on the correlation coefficient. All right, correlation coefficient is used as a measure of correlation between two variables. In this case, we are measuring between signal and concentration. Okay, so correlation coefficient is to estimate on how good the experimental points fit a linear curve. Okay, now we have looked here experimental points. Okay, when you look at this curve, these are all experimental points. Experimental points means that from 1 ppm to 5 ppm, you dilute this from your stock solution. Okay, from your that 1000 stock solution, 1000 ppm stock solution, you dilute it to become 5, 4, 3, 2, 1 ppm. Okay, and then you do your analysis. So basically these are the responses. So all of these are obtained experimentally. All right, so based on this, to estimate how good n of the experimental points fit the linear curve. So based on this pula, when we look at this curve, it shows that it fits more or less 99% good, because there are one points here that only touches the straight line. Okay, only touches the straight line due to the random error. So basically you would not be able to get a perfect apa a perfect straight line where the straight line passes through all of the points lah. But the correlation coefficient would measure how good the experimental points fit the linear curve. All right. So usually for this R value here, okay, R value here, it looked at the range of -1 or +1 lah. So kalau for example for this one, this is a +1. Okay, because for if it is a -1, it will be some sort like a downward pattern lah. Okay. All right. So the closer the R value to 1 or -1, the better the correlation between Y and X. Okay, so you look here, +1 or -1, perfect correlation lah. So that's what we are trying to aim. Okay, R must be near 1. Doesn't matter -1 or +1. Okay, so the correlation coefficient here it is stated that R of must be more than 0.999, which is it is apa? It is near, very near to 1, which is if it is among this range 0.99, so it can be acceptable for acceptable to show that your experimental data fit your linear curve. Okay, so now what is our aim? Our aim is that to get the calibration curve to become 0.9999, because you would not be able to get one. One is in an ideal world lah, without random error, but we are not living in an ideal world. So basically, you need to your aim is that to be able to get R to become 0.9999. That's your aim. Okay, up until this point, do you guys understand on how to look into the calibration curve? And what is your aim and objective in terms of when you do your calibration curve later on? Understand that? Okay. All right. So, okay, maybe I'll look into this one. Okay. So, when you look at this first this first graph here, you would see that the R is +1, or usually we look at R square lah, okay? R square is 1. So, do you think R square is 1 is okay? Anyone? Anyone want to try whether R square equal to 1 is okay?
Yes, doctor.
Okay. R square, thank you, Go. All right. So R square equal to 1 is okay, but you would not get that. As what I've mentioned before, R equal to 1 or R square equal to 1 is in an ideal world without random error. You would certainly have an error during your sample, your standard preparation and also your analysis. So R square equal to 1 is the one that you want, but it will not happen. Okay. Because due to the random error, it will be less than 1. But we need to be nearest to 1 lah. That's our aim. Okay. So between these two, R square 0.9962 and 0.9809, whether these two is acceptable ataupun tidak? Anyone?
Yes, Doctor.
Okay, which one is acceptable? Both ke ataupun salah satu?
Both acceptable, Doctor.
Both acceptable. Okay. All right. So, okay. when we look at into this table, we want to be able to get r square or r equal to more than 0.999, which is near to 1. As I mentioned, 0.99 kita nak, but 1 kita tak boleh dapat due to the random error. Alright. So for this one, usually 0.99 whatever behind it is acceptable. But if it come to 0.98, then you would need to do your calibration curve again, because it has much more error as compared to this one, to the first one, which is 0.9962. 0.9809, it is advisable for you to do your calibration curve again because it has much more random error as compared to the first one. So usually we will have 0.99 and whatever value behind it, but 0.98, it is advisable to do your calibration curve again. Okay, understand?
Yes, Doctor.
Yes.
All right, thank you.
Understand.
So yes, this one is an r square equal to not r square lah, r equal to -1 correlation. So this is r square equal to 1 lah. When you square it, it become 1. So this is also a perfect negative correlation. All right. But as I mentioned before, perfect, which is -1 or 1, will not be able for you to get lah because due to the random error. All right. So for this one, r square equal to 0.0112. This shows that this is a very poor correlation or no correlation at all because of this value of r square. And even when you look at it, the straight line doesn't passes through all of the points. It doesn't pass through any of the points. So this shows that this is not a good or very poor calibration curve. All right. All right. So now we look at into the calibration methods, which in terms of finding the best straight line. Okay. Many analytical methods generate calibration curves that are linear or near linear in nature. Okay, linear means that that's what you get lah, r square 0.999. Sorry, linear is 1. Near linear is 0.999 lah. Okay, so usually we want to achieve that. Okay, so this straight line, when you have r square is equal to 0.99 something, so you have an equation of the line, which is y equal to mx plus b. So I think that this equation you have crossed over this equation during your, I think your secondary school pun you dah belajar benda ni, you have looked into this. Okay, so y mx plus b is the equation for a straight line where your y is your dependent variable, x is your independent variable, m is your slope, and b is your y-intercept here. Okay. All right. So I don't think that we need to go into depth on this equation lah. So usually when you do in Excel, when you have your data points and you create your calibration curve, it will generate r square and also it will generate your straight line punya equation. Okay. All right. So now the goodness of the fit. Okay. So this I've explained before in terms of we look into the r square. So this is the explanation lah. What is r square? So r square compares the sum of the variation of y values to the best fit line relative to the variation to a horizontal line. Okay. So basically, this is what you want, 0.99 something. Where it passes through most of the points. If it is not most of the points point, it is balanced between the top part and the bottom part of the line. Okay, for this one, this is very poor correlation. Okay, r square is 0.5. Okay, very weak or no relationship at all, right? So this is your aim when you produce your calibration curve later on. You would need to be able to get something like this. If not, if you get something like this, then you need to do your calibration curve again. All right. All right. So how are you going to do your calibration curve? Okay. Okay. So how are you going to do your calibration curve? So your calibration curve, as what I've mentioned before, you need to prepare a known samples of analyte which covering the convenient range of your concentration. Okay. Prepare a known sample. Prepare a known sample ni prepare a known concentration lah of the sample. If you, as you said that we have used the apa? Use the standard analyte where you dilute from one, maybe let's see 1000 to maybe 100 ppm, and then you dilute it again to 10 ppm, and then you dilute it again to 1 2 3 4 5 ppm. Okay, so prepare a known sample with a convenient range of concentration. Convenient range here means that you need to know on the detection limit or the maximum limit of the instrument that you use. Okay. For example, when you do AAS, for example, when you do AAS, for a particular for a particular hollow cathode lamp, which is for a particular analyte, it is said that, okay, for this analyte, for this particular hollow cathode lamp, the maximum or the linear range would be maximum at 2 ppm only. Okay, this is stated in the apa uh, when you want to install your apa when you want to install your hollow cathode lamp. So it is stated that the linear range would be at 2 ppm maximum only. So with that information, when you want to create your when you want to create your calibration curve, it needs to be below than 2. So you need to do 0 0.1, 0 0.5, 1, 1.5, and then 2 ppm. So you need to know the range of concentration corresponds to the instrument that you are going to use. Okay. After that, when you have done, when you have determined the range, and then you do your your dilutions, and then you measure the response, and then the response must be able for each of the analysis, for each of the calibration curve, you need to have a blank as well. As what I have mentioned before, blank is important for you to be able to get zero response from the analyte. It's because your blank would be free from analyte. Okay, let's look here. Subtract average response of blank, which is no analyte. So sometimes your blank would create some sort like a response. But that response does not correspond to your analyte, because when we say blank, straight away no analyte of interest inside the blank. So whatever response that you've got from the blank, you need to subtract it later on. Okay, so let me look into an example here. Okay, all right, you look here. This is the concentration of the blank, which is supposed to be 0 ppm lah, because it doesn't have the blank. Sorry, it doesn't have any analyte, but it gives the intensity of 4.5. Okay, so whatever concentration, whatever response that you've got from the concentration of your from your calibration curve later on, from 0.2 to 2.5, whatever intensity that you've got, it needs to be subtracted this 4.5 for you to be able to create your apa for you to be able to create your calibration curve later on. So you have deducted or subtracted the blank the blank signal. Okay, faham tak for this? Sometimes your blank would be absent of your analyte, but it will give some sort like a signal as well. Okay, faham tak benda ni? Where you need to subtract. Okay, Ho Yi Ning said faham. Alright, good. If you guys have any question, you can straight away ask me. Stop me and ask me straight away. Alright. Let's move on. Make graph of the corrected response. This is what I said. Corrected response. So after you measure your blank, you measure your 0.1 ppm. You measure your 0.5. You measure your 1.0, 1.5, and 2 ppm. Whatever value that you've got from your calibration curve results, you need to subtract with your response of the blank, which is the corrected response, we called it. Okay, and then determine the best straight line. All right. Okay. In a calibration curve, we prefer the calibration curve with a linear response. Okay. So how you measure linear? By R square. Okay. And then analytical signal is proportional to the quantity of analyte. So when it is linear, we can say that the signal would be proportional to the quantity of the analyte present inside the calibration solution that you have created before this. Okay. Linear range. Okay, linear range is the analyte concentration range over which the response is proportional to the concentration. Okay, that's what I've mentioned before. And then there is a dynamic range as well. Okay, dynamic range, you would need to look at dynamic range is after the linear range. It we still have an increase in concentration or increase in response, but it's not linear anymore. Okay, it moves like a slant here, where at some point you would have you will have a constant value after this. So basically, in terms of quantification, we would have a linear range, but there is also a dynamic range where you don't use this range for quantification. Okay, dynamic range is a concentration range over where there is a measurable response to the analyte. It's still measurable, but it is not directly proportional anymore. Okay, all right. Okay, so when you have your calibration curve, when you do your analysis, you notice that okay, it seems like for this one, you look at this you look at this curve, this first curve. You look that oh okay, the first, second, third, even until the last point, it looks like it's quite okay lah. In terms of the it's still increasing, and you can think of some sort like maybe a straight line move between them. But suddenly you have an outlier here. Okay, outlier. So now we are going to look into the impact of bad data points, which is we call outlier. For some reason, maybe for this concentration, you have wrongly do the dilutions, or maybe in terms of your analysis, you have wrongly do your analysis for this point only. So when you plot when you include your data here, straight away your R square will become 0.5. But if you remove the outlier, it will improve the R square value straight away to become 0.99. Okay? So basically, you would be able to omit the bad points if much larger than average ranges and it is not reproducible. Okay, you will be able to omit or delete the bad points, or we can call it data points, the outlier points, if um, it is something in the middle of the range. Okay, it does not minimizes your range, but it does not, it will improve your R square value, where you'll be able to have much more better linear range here. Okay, is that clear for the bad data points outlier here?
Doctor,
Yeah.
the bad point we can just remove it.
Yes, you can
Just let
remove it.
remove it just like that.
Because all of this, the graph is something that you do in Excel, okay, or in any kind of other software lah. But your data here, you can just delete it lah. So you get your R square value much more better. But you need to also need to think about whether the outlier is an outlier. Okay. For example, for I would like to look at this point mana. Okay. Okay, for this data, whether this is an outlier, adakah semua ni outlier?
No.
No. Yes. So all of this is not an outlier because it acts randomly. For this one, when you look at it, only one point does not fit with all of the other points. So for that one, we can call it an outlier. Okay, bad data points can skew the best fit line and distort the accurate interpretation of the data. So if all of the points, okay, for example, for this point is here and all of the points is haywire, then it means that it is not an outlier, it is your skills, your dilution skills, your instrumental skills, okay? Not the fault of the data. But when you look at this data, you can see that, okay, everyone here, every points data here, it follows the same, more or less the same the same pattern, but there is an one point here which disturbs your best fit line. So you need to be able to determine also whether the points is an outlier ataupun tidak. Kalau banyak sangat tu bukan outlier lah, basically something like that. Okay, kalau if the majority of your points is when you say that the majority of your points is an outlier, then the points is not an outlier. Your skills, you need to create back your calibration curve. Alright. Okay ke Nur El Ain?
Okay, Doctor.
Okay. Alright. So, okay. So, determining the unknown values from the calibration curve, as what I've mentioned before. Okay, as what I mentioned before, knowing the the slope and the y-intercept will allow the value of x to be determined once the experimentally y value is known. So when you have done your experiments, you would get your data, you would get your r square and also your straight line equation. So from that equation, you can straight away determine what is the x, the concentration of the given the given response from your unknown, right? So basically, your unknown would give some sort like a absorbance. Okay, so maybe your unknown gives 0.2. So you move it towards the middle of the graph, hit the calibration curve line, and then you move down onto your amount of protein here with your x-axis, and then you've got your concentration of your unknown. Or you can do it by calculation as well. Okay, based on the straight line equation. All right. Okay, up until this point, do you guys understand about calibration curve? Okay, all right. Okay, can we have a 5-minute break? Boleh ke? Boleh, all right. Thanks, yeah.
Yes, Doctor.
So, we come back at 11:53 lah. Okay? You guys ada dengar bunyi drilling tak dekat saya punya audio?
Tak doktor.
Tak eh? Okay, alright, thank you. Okay, so 11:53 now, so maybe we can start back our lecture. Alright, so as what I have mentioned before, there are two types of calibration. There are three types, but in this chapter, you are going to look into two types of calibration curves. All right. So the first one is the standard calibration curve, which is the one that we have looked into before this, which is called an external method. Okay. External calibration method. Okay. We'll just put it there. External calibration method. So this is the common method that we have been using in terms of creating a calibration curve. So it uses one or more external standards containing a known concentration of analyte. We call them external because we prepare and analyze the standards which is separates from the samples. Okay, so basically the standard or the calibration curve is independent of your sample. Okay, so we create the calibration curve. For example, when you want to have a copper calibration curve, so you will need to dilute copper from your copper standard and then you create a copper calibration curve. If you want to have a plumbum calibration curve, you need to get your plumbum standard and then you dilute from 1000 to whatever range that you want. Okay, so that's why I said external calibration curve here that we have looked before is independent of your sample. Okay, there is another type of calibration curve which is called standard addition method calibration curve, which is this one. Because the matrix of the sample would create some sort like a distortion to the, or would create some sort like an interference towards your analyte response. Okay, this is what we call matrix interferences. Okay, or matrix effect lah. So with these metric effects, it will make your signal and the analyte signal much more higher or much more lower because your your standard calibration curve, there is no matrix effect involved. Okay, so you assume that there is no matrix effect means that the signal that you've got from your sample is free from any matrix effect because your standard calibration curve does not have the matrix. Okay, but for standard addition method, you assume that the matrix would have an effect. So your calibration curve needs to come from a point of view or where you would need to include those matrix effect. Okay, because understand between the difference between these two. The standard calibration where it is the external calibration where it is independent, no matrix effect, but with standard addition method, we from the point of view of we have a matrix effect.
So doctor,
Yes,
for the standard calibration, is that the one we discussed just now?
yes. So the standard calibration is the one that we have discussed before this, where you need to prepare 1, 2, 3, 5 ppm. Okay, but it is independent. It is not with your sample, kan? So because uh you prepare from your standard stock solution that you've got from the one that you purchase. Okay, it is independent of your analyte. Of your sample lah. But for standard addition method, kita akan create a calibration curve with your sample because we assume that the matrix would have an effect on your signal later on. You will see the differences later on lah. But I would just want for you to understand that external calibration method is independent of your sample, which means that there are no matrix effect. You assume there is no matrix effect, but for standard addition method, you assume there is matrix effect. So your calibration curve needs to come from your sample itself, which we will look later on lah on how to do this. Okay. Okay, now we look at external calibration curve, the first type of calibration curve that I have mentioned before and we have discussed before this. Okay, so now this, for example, when you look at this picture, you will see that, okay, the first one apa? The first volumetric flux ni, you rasa apa? Any guess? This is a zinc standard solution. Any guess? Anyone? The first volumetric flux here. What do you think it is?
Is a region blank?
Yes.
Or
Good go. So basically, the first one is the reagent blank. So when you see that, okay, for example, you can see that the color increases kan from left to right. Okay, so the first one is your reagent blank, which is free from your analyte of interest, which is in this case zinc lah. Okay, so you prepare all of this sample. For example, based on this table, you can see that this is 1, 2, 3, 4, 5 ppm of zinc standards in this volumetric flask. Okay, you do your analysis, AAS, for example, you've got your concentration here. For reagent blank, you've got 0.05 absorbance. Okay, so you need to ensure that for one concentration here, for 1 ppm, the absorbance is 1. And you need to, apa, this one, this number one, one absorbance here is already been subtracted with 0.05. Okay, because we need to subtract the absorbance of the blank to get much more better apa linear range. Alright? Alright. Then let's say you have a tap water sample containing zinc, which is sample A. So it gives the value of absorbance 3.5. So how would you get your absorber concentration of your sample A? You can use either your apa equation here, which is you just input 3.5 at y here, which is the absorbance, and you can compute your x here, or you can, yeah, that is much more better lah to use the equation. If you can see here, 3.5, you want to, you don't know where the apa the point is, so basically you just use the equation to get your concentration of unknown sample A. Alright. Is that understood for the external calibration curve? You prepare your your standard calibration curve, which is independent of your sample A. So sample A ni tak ada kena mengena dengan you punya calibration curve. So we assume that the matrix in this sample A ni does not have an effect onto the zinc punya signal later on. So 3.5 ni does not have a matrix effect punya effect. Okay, understand tak? Understand ke? Buka lah mic tu, cakap lah ya.
Okay, doktor.
Okay, barulah ada respon. Saya pun taklah cakap sorang-sorang. Okay, alright. So basically, this is what I've mentioned before on how to do the external standard calibration. So the standard and the sample are analyzed separately under identical conditions. It is analyzed separately means that it is independent of each other. Okay, the blank must be subtracted, which is what we have looked before, and then the calibration curve, which we have apa the equation obtained from the calibration curve, and then we can use this this equation to know the amount of the analyte of the sample lah, of the unknown sample. External standard calibration is feasible is the standard and the sample matrix has no effect. Okay, so this is important. Okay, when you assume that the matrix has no effect, so you straight away do external standard calibration method. Okay. If you think that the matrix have an effect, then you need to do a standard addition method later on. We'll look into it later on. Okay. All right. So basically, this is the external standard calibration method. What are the general procedures lah? This is something for you to know about. All right. So basically, measure the response of the reagent blank. So basically, you need to have blank. Blank is important because the signal produced by the blank, you need to subtract it. Okay. First of all, measure the blank, whatever the value of the blank, subtract it by your signal from your standard curve. Okay. All right. So the second one is that measure the response. Okay. So basically, you need to ensure that R square is equal to 0.99 XX lah. Okay. This is the best one that you can that you can get. Okay. All right. So now measure the response of the QC. So for sometimes when you have your calibration curve, okay, maybe after 10 or usually after 10 analysis, you just try to do a QC quality control punya analysis where you just put in your, for example, you put in 5 ppm of known concentration, and then you look at the signal, whether the signal is still okay or not. Kalau if there is a fluctuation in the signal, if the fluctuation is very large, so the QC values must be between 95 to 105% of the true value. Okay, the RSD must be less than 10%. If it is more than 10% or it is less than 95, more than 105, that means that your calibration curve doesn't work anymore. Okay, because the instrument itself has its own deviation. Okay, instrument ni when you, yelah, benda yang kita dah guna banyak kali, when we have used it so many times, so sometimes it create a deviation. Okay, so you need to do your calibration curve again. Okay, so measure response of the sample. After 10 samples, it says here after 10 samples, redo the measurement of the QC response. If it is still between the ranges here, continue the measurement of the sample with the with whatever sample that you have lah. If the QC values falls outside of 95 or 105 and RSD is more than 10%, so you need to redo your calibration curve again. Okay, so measure the new response to with the new calibration plot. All right. So all of the measurement will need to be taken in triplicates. As I mentioned earlier, triplicate analysis is the norm, okay, of the analytical procedures lah. All right. So up until that point, okay ke? For the standard external calibration. After this, we are going to look into the example lah. Okay tak? Okay kan? Alright. So if any question, just stop me straight away, yeah? Alright. So for this example, we are going to look at okay, now we determine the concentration of analyte in the sample given the data in column 1 and column 2. Alright. So when we look into the data here, we see that first of all, you straight away look at the intensity of the blank. Okay, you straight away do the subtraction later on lah. Okay, so 11 minus 4.5, 21 minus 4.5, and so on. All right, so, and then after you have done your calibration curve here from 0.0 until 2.5, you create your calibration curve in Excel, and then you do your sample analysis. Your sample analysis give the intensity of 63. So, how does it work? Okay, anyone want to try to explain on how to do this? Ada ke nak try? So you have your data. So this is the plot. Okay, this is the plot. So anyone want to explain macam mana from 63 intensity to how are you going to get your concentration of your unknown sample? Anyone want to try? Explain je, tak ada masalah. Tak ada nak try ke? Kalau tak saya panggil nama.
Doctor, boleh saya try?
Okay, boleh. Sharvin, thank you.
Maybe we could just interpolate from the graph, or we could just substitute the value into the equation.
Alright, so basically, when you have your sample gives 63. So 63 two goes where?
It goes in the y-axis.
Okay.
Yeah.
So y-axis, and then you got your x. So x is the your your unknown concentration lah.
Yes,
So
sir.
that's how you do this. So for example, when you do your any type of instrument later on, you've got this data. You got this data, you subtract it already in your Excel. Then you straight away create this kind of calibration curve. It is straight away give you R square and the y value, the equation line lah, the line equation. So you've got your sample and you just use the sample use the value, the peak intensity from the unknown sample to get your unknown concentration. Okay. What if I want to ask, what if your analyte your unknown concentration give the intensity of 150? Any guess? It gives for example your analyte your unknown give 150 intensity. So what do you think would happen? Sharvin, any guess?
If the concentration is 150, Doctor,
Uh-uh.
then just substitute inside the x to obtain the one. Is it?
Okay. So now, when you look into this when you look into this calibration curve, and then the one that you have made, kan? Okay, the one that you have made, the intensity is from 0 until 82. So when you create your calibration curve, your it is linear from 0 to 82. Okay, it is linear from 0 to 82, which gives this equation and which gives this R square. So when your sample, when you analyze your sample, it gives a value which is out of the linear range, out of the range that you have done before. Because your range is until 82 je, tapi the analyte, the sample, the unknown sample give a response at 150. So it means that you cannot use this calibration curve, because your calibration curve is plotted until 82 only, which is until 2.5 ppm. Means that your response for your unknown concentration now is in the dynamic range, which is outside of your linear range. So basically what you need to do, kita buat apa, Shavin, kalau dalam case ni?
We have to extrapolate the graph.
Okay.
Wow.
Extrapolate should not be done, because extrapolate means that you just continue this straight sampai atas, kan? Which is should not be done. You need to extend your calibration curve. So means that you don't need to stop until 2.5 only. You need to do until maybe 5.0. Okay, you extend your calibration curve until 5.0, and then you've got a new a new equation and a new R square, where it is included in your unknown concentration tadi, unknown response tadi, which is at 150 intensity. So this is what I want to show you guys is that whatever analysis that you do, it needs to be in your linear range. Your signal from your unknown must be in your linear range for it to be able to use this equation. So your analyte must be between 0 until 82 only. If it is out of 82, it is more than 82, you need to extend your calibration curve, which will comprise of the intensity tadi itulah your unknown. Okay, understand tak?
Yes, Doctor. Faham.
Okay, alright. Thank you. Okay. Alright. So this is for the ICP OAS and ICP MS spectrum. So basically, before this, kalau kita tengok AAS, the analysis is one by one kan? Analysis is element by element. But for ICP OAS or ICP MS, it's usually multi-element punya analysis. So basically, it's still the same. You still need to have the calibration curve from each of the analyte. Okay, so for example, for this ICP MS, you have a couple of 6 of calibration curve here of corresponds to each of the analyte. Okay. All right. So this is an example of a calculation. Maybe I give you 2 minutes to look at it first. All right. So we look at this calculation. Example of calculation lah. Alright, a spectrophotometric methods for the quantitative determination of plumbum 2 plus levels in blood yields and absorbance of 0.474 for a standard whose concentration is PB is 1.75 microgram per liter. So now you have got your absorbance for the standard. Okay. So for standard of 1.75 microgram per liter, the absorbance is 0.474. Calculate the PB occur in blood samples if the absorbance is 0.361. Alright. So basically, this is the formula for you to use lah. So basically, you need to know the slope first, which is the slope will become as 0.474, which is the absorbance divided by the standard corresponds to the absorbance ni lah. So you've got the slope of 0.2709. And then in terms of the unknown concentration, so it gives you the absorbance divided by the slope. Okay, it will got 1.33 microgram per liter. Okay, so this is how you are using you are using this data to get the slope and furthermore to get the results of the concentration of the unknown lah. Okay, all right. So now we are going to look at the matrix effect. Okay, tadi when we look into the external calibration curve, I've said that we assume that there is no matrix effect. Okay, so now what happens when there is a matrix effect? Okay, in chapter 1, we have looked what is matrix actually. Matrix is everything in the unknown sample other than the analyte. So analyte is your interest. Other than your analyte is the matrix. So what is the matrix effect? So this matrix, which is other than your analyte, will cause a change in the analytical signal. Okay. So the value of the slope versus the matrix effect. Okay. For example, now we are looking at analyzing groundwater as compared to in reagent water. So you can see that if it is in groundwater, you see that the calibration curve is the curve is here, where if you assume that there is no metric effect and you use only in reagent water, then this is the calibration curve. So it shows that there is a difference and there is a magnitude here where the matrix would have an effect onto the signal produced by your analyte. So based on this, we are looking into a couple of things lah in terms of how to avoid this metric effect, right? All right. So option in terms of overcoming this metric effect. So we are looking into matrix matching, standard addition, and standard addition single spiking with standard. And the third one is standard addition calibration method, the one that I have mentioned before. All right, matrix matching. So basically it goes without saying lah. By its name pun, so adjusting the matrix of the external standard so that is the same of the matrix of the sample to be analyzed. Means that the the matrix in your external standard calibration curve too, the one that you have prepared earlier must match with the matrix of your sample. So in this case, for example, use synthetic seawater to prepare diluent in standard solution when studying seawater sample. Okay, so you use synthetic seawater sample. You use synthetic seawater to prepare your external calibration curve, and then your sample put is come from the seawater. So the matrix match. So that's what we call matrix matching. Okay. When you have this matrix matching, you can straight away use your external standard calibration because we have factored in your matrix into your external calibration curve. Okay, that's the first one. The second one is the standard addition single spiking with standard. Okay, so before this, one of you have asked me in terms of what is spiking. Spiking is you put a known amount of your analyte into your sample. For example, your seawater sample that just now you have unknown you have you don't know the value. Okay, so you spike in your known amount of the same analyte into the sample, and then you straight away do your calibration curve. Sorry, you do your analysis, and then it gives out the value. Okay, so that's how what is called as spiking. So we spike a known amount of analyte into known concentration of analyte into a sample, right? So the third one is the standard addition calibration method. Okay, this is the one that we are looking into after this. All right. All right. So a single point spiking method. So the protocol to determine the quantity of an unknown is that the known quantities of an analyte are added to the unknown. So this is what I've mentioned before. The known quantities of the analyte is added to the unknown. Okay, known and unknown are the same analyte. So it needs to be the same analyte lah for this to work. Okay, it increases the analytical signal which is related to the total quantity of the analyte. Okay, for example, I give you an analogy. 1 ppm create a 5 signal. Okay, 5 absorbance. Okay, so 1 ppm standard would produce a 5 signal. Then you do your single spiking method. You know that you put 1 ppm inside the sample, and then you've got about 10 signal after that. So secara tidak langsung, you can know that 1 ppm is equal to 5. So where is this other 5 comes from? It comes from the sample itself. So those sample, it comes from the sample. So the extra 5 corresponds to 1 ppm as well. Okay. Between that analogy, did you guys get it? But we do have this we do have the equation, but the analogy is like that. When you put the known quantity, you know the response, but sometimes, but usually it will create an extra response. So those extra, the differences between the known and the unknown is your unknown punya response lah. Okay. So it measure the signal which is directly proportional to the analyte concentration. So it is done by having this the equation lah, concentration of analyte in the initial solution divided by concentration of analyte plus standard in the final solution, the signal from the initial and the signal from the final solution. All right. Maybe we look into the example for you to be able to know, to understand this much more better. All right. So serum containing sodium ions give a signal of 4.27 MV in an atomic emission analysis. Okay, now you know that Na from the serum give 4.27. So 5 ml of 2.08 molar sodium chloride were added to the 95 ml of the serum. So 5 ml, 95 ml, it creates 100 ml. So the spike serum give a signal. So this is called spike lah. Okay. We add this sodium 5 ml of sodium chloride into the 95 ml of the serum So the spike serum gives 7.98 MV. Just now the serum only the serum is 4.27 MV. The spike one 7.98 MV. How much Na, how much sodium ion was in the original sample? Okay, so basically based on the equation, so you can compute this equation based on this equation. You compute the data, and then you've got your sodium ions is 0.113 molar. Okay. So that's how you do the single point spiking. All right. Okay. Now we are going to look into the standard addition calibration curve method. All right. So the standard addition calibration curve method, I think that I'm going to use this one. All right. The standard, which is identical to the analyte of known quantity, is added to the sample and calculated from the response obtained. It is suitable when the composition of the sample is unknown or too complex, or there is a variation in the response due to the matrix effect. So standard addition method, the calibration curve comes from the sample itself. Okay, where you spike your sample with a known amount of standard. All right, rather than do single point spiking ataupun you do your external calibration curve method tadi. So now, based on this, this is your sample lah. Basically, all of these are the sample. So the first one is x plus 0. So means that this is only your sample. X plus 10 ppm. So this is X plus, means that your sample plus 10 ppm of the standard. X plus 20, X plus 50, X plus 100. It depends on how are you going to do it. And of course, we need to have a blank as well, which is without your analyte. All right. So how does this work? So at the same volume, okay, so where is it actually? All right. So this is your sample, this is your solvent. Okay. So sample and solvent, this is X plus 0 lah. So the standard is 0 here. But when you put your standard in 1, so the concentration is still sorry what is it? Okay. All right. So this one is X plus 10. 10 here is the volume of the standard. It is not the different concentration. So for when you look at this one, the standard solution is at 10 ppm. So you use those 10 ppm, but different different volume into each of the standard calibration, standard addition method. So, for example, for those 10 ppm, 10 part per million standard, for the first one, you don't put any volume. The second one, you put 10 mil of 10 ppm. The third one, you put 20 mil of 10 ppm, and then this is 50 mil of 10 ppm, and then the fifth one, you put 100 mil of 10 ppm. It is not the difference between the, it's not the difference in the concentration of the standard, but it is the difference in terms of the volume. Okay. When you look into this figure, you would see that this is sample, this is your solvent, kan? Sample, solvent. So the sample is the same. Everything is 5 mil, 5 mil. Example lah, 5 mil, 5 mil, 5 mil, 5 mil. Alright? So the standard that you put it in, the red one, you put it in at 0. So this one is 0. This one is 1. 1 mil lah, for example. This one is 3 mil. This one is 4 mil. So there is an increase in volume of standard, not increase in the concentration of the standard, because the concentration of the standard is still at 10 ppm. So end up, we would get a total volume of 10, 10, 10, 10. Okay, understand tak for this one? Guys, understand tak?
Doktor,
Ya.
kalau increase volume tu dia increase, tapi total volume dia masih sama lagi.
Total volume masih sama. So end up, all of the volumetric flux would be 10 mil lah, for example. So 10 mil. So when you put in your sample 5, so your solvent 5. But in the second bottle, sample 5, standard become 1, and your solvent become 4. Then, so the last one, 5, 4, 1. 5 for the sample, 4 for standard, 1 for the solvent. So you increase the amount of the volume of the standard.
Oh, understand. Oh,
Okay.
thank you, Doctor.
All right. Thank you. So anyone else have any question? Faham tak? Okay. All right. So when you do your analysis, okay, so all of this tube will be subjected to the analysis lah. So when you do your analysis, sekejap bagi saya 2 minit jap. Alright, sorry. So when you do your analysis, your first tube here, which is your sample, only your sample lah kan, sample with a solvent lah. So your sample, so the concentration, the standard addition method here, the calibration curve is analytical signal, which is the same. But for this one, the x-axis is the concentration of added analyte. Alright, so the first one, the first one here, the concentration of added analyte is 0 lah, because there is no standard added. The second one, the concentration is going to be different because the standard, even though it is 10 ppm, but it is only added 1 mil, for example. Okay, this is 3 mil, this is 4 mil. All right, so the response would be increasing, an increasing pattern, because we do increase the volume of the standard. So it's said here, readings obtained with the standard, with the added standard. Reading of unknown without added standard. Okay, so you have your intercept. You will have your straight line here, and you have your intercept here at an increased point lah. It will not be zero because your sample here without the addition of standard pun would create some sort of like signal. That's what we should expect. Okay, so this line is due to the standard that you have been added before with different volume. Okay, so these readings would create some sort like a straight line, some sort like a straight line. So for you to be able to know the concentration of your unknown, because this is our aim after all, we want to know the concentration of our standard of our uh, unknown sample here, the first one. So what you need to know, what you need to do is that you extrapolate. For this one, you can extrapolate. Okay, you need to extrapolate back to the x-axis, which is in this case, it has given negative 0.04 because it is at this side of the graph lah. Okay, but this extrapolation pun is going to be governed by this line. So that's why you need to have this line, because sometimes it can be apa? Let me draw. Okay, sometimes your standard might be like this. The line can be like this. So the points here, 1 point here, 1 point here, and 1 point here. So it govern like this. So your extrapolation would become like this, some sort like this. So that's why I said it can be extrapolated, but it needs to be governed by all of the points that you have gathered earlier by the addition of your standard. So this is the concentration of your unknown analyte, of unknown sample. Okay, up until this point, understand tak? Of how you do this. Understand, yeah, Iza? Okay, alright. Because this is very important, yeah. This is important. This is the usual examination question lah. For you to be able to know on when to use it and how to use it. Okay? Right. Okay. So for this one, also the standard addition, as I mentioned before, this is the reading without the added standard. This is the readings of this of the standard that we have added earlier. Okay. Sekejap, Alright, so when you have this intercept also is governed by your by your readings here lah. So that's why you can extrapolate to the unknown concentration here. Alright, so that's how you do it lah. Okay, so when we look into the example, in terms of how are you going to determine the concentration, so these are x plus 0, what is the response? So this is the unknown punya response lah, the unknown punya response. This is the response by addition of 10 of your standard. So when you do your standard addition graph, you would have this some sort like this graph. So you can extrapolate to become at this point. So this point, the negative x is the concentration of your x plus 0 here. The concentration is negative x. Okay, the one that we have obtained here. Alright. Okay, so up until this point, understand tak? Ada apa-apa soalan up until this point?
No question, okay.
Siapa yang bercakap tu tak dengar? Imran.
Imran, okay. No question.
No question. Okay. So, alright. So, I think that we can stop here. The remaining of the lecture, I will, because there are some things that I need to add into this lecture later on, but I will make a video out of it lah. So, I will put inside your e-learning. Alright. So, for this Thursday, you have your second quiz kan? You have your second quiz. Ni kejap ada soalan. How many question will be in the quiz? I don't know yet because I have not done the quiz questions yet. But it will come from chapter 3 and chapter 4 lah, which is your AAS and your ICP OES and ICP-MS. Okay? Alright. So sorry. So on Thursday, because through this online, the quiz will need to be done, I think 9:10 until 9:50 lah, because 30 minutes to answer the question, 5 minutes to download, 5 minutes to answer, 5 minutes to download and 5 minutes to upload, which is about 40 minutes. So I think that maybe on Thursday we don't have a class lah, but I will provide this lecture later on for you to be able to look at. Okay? This is not going to take long pun, about 10 to 15 minutes sahaja. So you can use that time to study for your quiz, or maybe if you want to look at this lecture pun tak ada masalah. Okay? So we will not have any classes lah on Thursday, but there is a quiz at 9:10 until 9:50. I already put that inside your e-learning, the notification, and then the question will be inside there as well. Alright? On Thursday. Okay, ada question lagi?
Doctor,
Yeah?
just to confirm for the upcoming test, our test is from chapter 1 to 3, right?
Test?
Yeah,
No, test is going to be chapter 1 until chapter 6.
Oh,
1 to 6. Next week is chapter 7, which is we have for this week, later on I provide the video. So for this week we have finished your spectroscopic methods. So next week we will start with chromatographic methods. All right. So your test would cover all of the spectroscopic method lah, chapter 1 until chapter 6, this chapter. Okay.
yeah, doctor.
Okay. The test consists of 4 questions, as for quiz is allowed to type. The test I also don't know yet how many questions is that, but the test would correspond to 50 marks. Okay, because the test would be 25% of your assessment, so it will be 50 marks. So the quiz also, we will maintain whatever that we have done before. Is subjective. You just download it. You whether you want to write it on paper pun tak ada masalah. You nak write it in your iPad ke tab ke tak ada masalah. Just upload it back in PDF form and ensure that I can see your answer lah. Okay. Alright. So if there is no more questions, maybe we can end our session. If there is more